All right, so today's notes are on sequences, and our content objective is to define, identify, and apply arithmetic and geometric sequences. Our language objective is to correctly describe sequences with terms including arithmetic, geometric, common difference, common ratio, term number, term value, and initial term. So first thing we're going to define is a sequence. So a sequence is an ordered list of numbers. So this is a really broad definition that includes more than what we're going to be focusing on today. So today we're focusing specifically on arithmetic and geometric sequences. Sequences can be any ordered list of number or any list of numbers with any list of numbers that is in a specific order. So, but we're specifically talking about these two types of sequences today. So I'm going to have us jump in with a quick check, and I want you to determine the pattern in these two sequences that I've written below. So see if you can figure out the pattern that's occurring looking from one term to the next. So each part here is called the term. See if you can figure out what it is. So hopefully you notice in the first one that the pattern each time is that you're adding 5. So each time you add 5, and that brings you to the next term. So 3 plus 5 is 8, 8 plus 5 is 13, 13 plus 5 is 18, 18 plus 5 is 23. So our pattern was that we add 5 each time, or we add 5 to get the next number. We started with 3. So 3 was our initial term. So this is our common difference. This is our initial term. And so because we're adding 5 each time, our pattern is going to be an arithmetic sequence. So because I was adding 5 each time, my pattern was differed by a constant amount. So I had a common difference. My sequence is arithmetic. The next one is slightly different. You may have figured out that it's going to be our other type of sequence, geometric. But what is the pattern that is occurring here? So what we're actually doing each time is multiplying by 2. 3 times 2 is 6. 6 times 2 is 12. 12 times 2 is 24. 24 times 2 is 48. So our pattern here was to multiply by 2 each time. So this is our common ratio, because it's going to be our other term. Again, we started with 3. So that is, again, our initial term. But this sequence is geometric. Because we're multiplying each time, it's going to be a geometric sequence. So arithmetic sequences differ by the same amount. We could be adding 5 each time. We could be subtracting 3 each time. We could be adding 1/2 each time. We could be subtracting 1/3 each time. The main key here is that we are adding and subtracting every time. So this is when you're adding or subtracting. Geometric sequences, on the other hand, are when you're multiplying or dividing. So here we multiplied by 2 each time. I could have been dividing by 2 each time, since that's the same as multiplying by 1/2. Hint, hint. So I could have been multiplying by 2 each time, multiplying by 20 each time, multiplying by 1/4, or dividing by 4 each time. All of those sequences would be geometric, because that's when you're multiplying or dividing. So arithmetic is adding and subtracting, geometric is multiplying and dividing. And so I decided to flesh out the details and differences between these two sequences a little bit more before we continue. So arithmetic sequences, you add the same common difference to get the next term. So when I say add, you could be adding a negative, which is the same as subtracting. So common difference, arithmetic, you have a common difference every time. These are pretty much just linear functions. So arithmetic sequences are just linear functions. But they have only whole number inputs, because we'll get to the details of how we come up with these formulas, but our inputs are going to be where it falls in the list. So because our input is where it falls in the list, we can't have a 1.5th term or a 7.8th term. So our inputs can only be whole numbers, since they represent spots in the list. or points in the list, so they can only be whole number inputs. But other than that, arithmetic sequences are just like linear functions. And then I provided the recursive and explicit formulas for these. So we'll talk about these in more details later. The explicit formula is going to be our focus for today. The recursive formula just defines it by the pattern. So it just tells you take a term and then add the common difference each time. So again, we'll go into detail with that a little bit later, but just to give you a gist of what that's about. Geometric sequences, on the other hand, you're multiplying by the same common ratio to get the next term. So again, this common ratio could be a fraction, which would make it appear like you're dividing each time. So if your common ratio was 1/2, you'd be dividing by 2 each time. If your common ratio was 1/4, you'd be dividing by 4. But the key here is that you have a common ratio that you are multiplying by each time to get the next term. These are just like exponential functions, but again, they only have whole number inputs because, again, the inputs represent a spot or a point on the list. So it can only be a whole number, the first term, second term, third term, fourth term, so on and so forth. The recursive formula, all you're doing is multiplying by the same common ratio to get the next thing. We'll talk about that more later. Explicit formula is what we'll be focusing on today. And again, you might notice that looks very much like our exponential function equation. Okay, so now that we've introduced sort of the basics of these two types of sequences that we're going to be working with, I'm going to flip the page and talk or go through some examples of what we might be doing with these. And we're going to be doing more than just the examples I'm showing you today in class, but this gives you an idea of how to use and manipulate the formulas that we're going to be working with. So the first example, I want us to find the 100th term in the sequence that goes 6, 11, 16, 21. So the first thing I want to do is talk about figure out what term or what kind of sequence we're working with. So you might have already noticed we're adding 5 again each time. That is coincidental. Your common difference will not always be 5, but I'm adding 5 each time. I'm going to ultimately try to use, or I'm going to use our explicit formula for arithmetic sequences. So I'm going to go through and define each of these variables. So the first thing, D, is our common difference. Which is in this case 5. So I know our common difference here is going to be 5 because that's what I'm adding each time to get the next term. So before I go into the other variables, I'm going to write out my list in a different way. So I know my first term in my list is 6. I know the second term is 11. I know the third term is 16, and I know the fourth term is 21. So the reason I'm writing it out like this is because this is telling us some key information. So the term number tells me what my n value is. So this tells me that n is 1. So if I'm looking at my n here, it's my first term. N is 2 is my second term, n is 3 on my third term, and n is 4 on my fourth term. So you could also say your first term, this is kind of like function notation. So A1 is 6. So I could write this like a coordinate point 1, 6. A1 is like your y, n is like your x. So it's this would be your n, this would be your A1. This would be, if we wrote this out, we'd have 2, 11. This again is n, and this would be A2. So A2. So again, this n tells us what point on the list we're talking about. So this would be n, comma, A3. And again, 4, 21, n, comma, A4. So again, these are like our x and y values, but instead of using x and y, we're using n and an is kind of like our function notation. We put this subscript in little and small on the bottom that tells us which term number we're talking about. So continuing on for the sake of time, I know that this part is my term number. last bit of vocabulary. And this bit is my term value. So again, term number is like your x, term value is like your y, your n and an are n and a1. So if I continue on defining my variables, I know my an that I'm talking about, since I'm finding the 100th term, sorry, is that too far up? I know I'm finding the value of my 100th term. So an is a100 because I'm trying to find the value of the 100th term. So I'm going to plug in 100 for n. Continue. I know my first term value is 6. I know, again, my n value is 100 because I'm finding the 100th term. So I'm going to plug in 100 as my input and get the value of the 100th term. And d is going to be 5, my common difference here. So then I can plug in my variables. So I know I'm finding the value of the 100th term. I know my first term value is 6 plus 100 minus 1 times 5. So again, I just plugged in to my explicit formula here, and then I can just evaluate out for a 100. So I have 6 plus, if you want to do this in your head, you can do 500 minus 5, which is 495, or you could do 99 times 5, either way, and then you get a 100 is equal to 501. So this would suffice as my answer. If I wanted to write out the answer, the value of the 100th term is 501, if you want to write that as a sentence. So I want you to try the last one on your own as a quick check. So I want you to find the 10th term of the sequence 4, 12, 36, 108. So pause it if you need to. I'm going to go over it now. So the first thing I'm going to do is figure out what is my pattern here. So 4 to 12, I don't have a common difference because 4 minus 12 is 8, 36 minus 12 is 24, so I don't have a common difference. You might be noticing that there is a pattern that you can multiply by 3. So I multiply by 3 each time. That means that the sequence I'm working with is going to be geometric, so I'm going to use my geometric sequence explicit formula. So I'm using this formula now since I've figured out that it's going to be geometric. So now I know my common ratio, R, is equal to 3. The rest of the variables are the same thing. So my first value in this problem is 4. I know the n value that I'm trying to find, this time is the 10th term, so a is 10, which means my an is a10. And then last but not least, oh, I already wrote R, just kidding. So that's everything that I need. So I can plug in my formula. I have A10 equals 4 times 3 to the 10 minus 1. If I plug that into my calculator, I'm going to get 78,732. So again, you can plug that into your calculator to get your answer. And then if I wrote that as a sentence, I'd say the value of the 10th term is 78,732. So again, this could suffice as your answer, but if you wanted to write it out as an explanation, that would be it. All right, last little thing. To prove that a sequence is arithmetic or geometric, you need to find the common difference or ratio 3 times. So here, I can't assume that this sequence is a geometric sequence until I see that there is indeed a common ratio 3 times, unless it's stated that it is. Same here, I define the common difference at least 3 times to make sure that is indeed the pattern. Otherwise, you can't make the assumption that it is arithmetic or geometric. All right, so that's it for today. Make sure you write down any questions, comments, or concerns you have so we can go over them together in class.